Hello and good morning. In this video, we are going to discuss two numerical on computing directivity and gain from HPBW. The concept of HPBW we have learnt in video number 2, that is in patterns. The statement of this numerical is the measured HPBW of an antenna in orthogonal planes are 30 degrees and 20 degrees. So there are two orthogonal planes, E plane and H plane, and this is only one angle theta. Phi angle is not mentioned here. So the angle theta in E plane is 30 degree and in H plane it is 20 degree. Here we'll modify this statement by saying compute the approximate gain of this antenna. So the solution of this problem starts with understanding of the two angles 30 degree and 20 degree, which are theta E and theta H. We have studied the definition of gain as product of efficiency and directivity. Now, since in this numerical statement the efficiency is not mentioned, if you know, efficiency is antenna radiation efficiency, which comes in three parts as radiation efficiency, dielectric efficiency, and the conduction efficiency. So since efficiency is not mentioned, we can assume it as 100%, so its value is 1. So here the gain that we are going to compute is nothing but the directivity. So now the task is to find out the directivity, and the approximate directivity of an antenna is given by formula 41,253 square degrees divided by product of these two angles in degrees. So theta E, which is 30 degrees, and theta H, which is 20 degrees, the product of these two in the denominator. So these two angles, since being in degrees, the product of this is degree square, so which is nothing but square degrees. So this is again a ratio of two identical terms, thus directivity is a dimensionless number. So we have D 41,253 divided by 30 into 20, which comes as 68.76, and the gain G is eta into D. Eta is 1, efficiency is 1, so the answer of gain is 68.76. So the gain in dB can be calculated by 10 log 68.76, which comes as 18.4 decibels. The second example is again to compute the approximate HPBW of an antenna, and in this case the electric field of the antenna is given by this equation 3 plus 2 cos theta. So we can see here again only one angle is mentioned, theta, and that theta angle is measured from the broadside. The broadside and end fire are two types of arrays, and we will be learning these types of arrays very shortly. So 3 plus 2 cos theta is the equation of electric field, and we need to compute the approximate HPBW. Again, the solution of this problem is by obtaining first the maximum electric field, because once we find the maximum electric field, it becomes easy to find out the half power beam width. So the maximum electric field is useful in computing the normalized electric field. So the maximum electric field, since there is a cos theta term, and for cos 0 the value is 1, we get the maximum radiation in cos 0 direction. If this equation comes as 3 plus 2 sin theta, then definitely we need to take the theta in 90 degree direction, because sin theta is 1. So since cos theta is given, we take theta is equal to 0 as the direction of maximum, and we compute the maximum value as 3 plus 2 cos 0. Cos 0 is 1, 3 plus 2, 5. So the normalized electric field is the given electric field 3 plus 2 cos theta divided by its maximum value, which is 5. Now for HPBW again we have studied in the pattern video. HPBW, the normalized electric field is always half of its maximum value. So the maximum value we have computed 5, and 3 dB below. Half is not 5 divided by 2 here. It is 3 dB below, and 3 dB below is 1 upon root 2, which is 0.707. So the normalized electric field in case of half power we get as 1 upon root 2. So equation 1 is the normalized electric field in major lobe direction, and equation number 2 is normalized electric field when HPBW is observed. So if we compute, or when we compare these two equations, we get 3 plus 2 cos theta by 5, equation number 1, is equal to 1 upon root 2. So this simplification gives us cos theta as 0.268 and theta as 74.5. Now if you have seen the pattern video carefully, this is a major lobe of pattern, and these are minor lobes, and this is back lobe. So this is the maximum value of electric field. 3 dB below it, somewhere here, we get these 2 points, and when we join these 2 points with the center where the antenna is placed, this distance is known as HPBW. Now the angle that we have computed here, 74.5, is only on one side of this radiation pattern. So this is 74.5 degrees, and if we need HPBW, we need to take the twice of this value. So the HPBW is nothing but 2 theta, 2 into 74.5, which comes as 149 degrees. So these are the two examples of computing gain directivity, and in this example we computed approximate HPBW. In the next video we will be discussing the computation of effective aperture and directivity of lambda by 2 and short dipole antenna. Thank you.